now comes back again. Okay.
Okay, welcome everyone. It is a great pleasure to invite you all today here and welcome you to the colloquium which will be given by Professor Karel Bender. And I would like to ask our scientific host, Sergey, to introduce our speaker.
Yes, okay, so good morning, everyone. Good evening, Professor Bender. Welcome from the future, as we can say now, and happy birthday to you, because in your day, which is the 18th of January, you have birthday today, so we wish you to stay healthy, first of all, productive as ever, and bring us many more scientific gifts, similar to the ones, I hope, which we will enjoy today. Let me now say a few more words about Professor Bender, whom many of us know from some, in particular from one of his papers. Let me first tell you a few words about his career. He's currently a Konecker Distinguished Professor Emeritus of Physics at Washington University in St. Louis, and he's a visiting professor at Heidelberg University, a visiting professor at Imperial College London, and also a visiting professor at King's College London. He, some time ago, received his PhD from Harvard University, and then he had various posts at the Institute for Advanced Study in Princeton, then having an associate professorship of applied mathematics at MIT. He was also an Ulam scholar at the Los Alamos National Lab, quite a well-known, I think, position also in or scholarship known in nonlinear physics, I guess. He was editor-in-chief, or maybe is, no, was, I guess, editor-in-chief of Journal of Physics A, and had a number of fellowships from Sloan, Guggenheim, Lady Davis, Fulbright, Leverhulme, and Rockefeller Foundations. He was awarded the 2017 Denny Heinemann Prize for Mathematical Physics, and currently has support from the Alexander von Humboldt Foundation and the Simons Foundations. Now, let me say a few more words about his outstanding scientific career, which counts, I don't know how many papers. I didn't have time. I'm sorry, it's very early in the morning to count them all. But what I can tell you is he has a stunning H index, which is about 70. And he has 37,000 citations to his work. And in particular, I want to mention this one work, which I became familiar with a long time ago, which is called Real Spectra in Non-Hermitian Hamiltonians Having PT-symmetry, from 1998, published in Physical Review Letters, together with Stefan Böttcher, who apparently visited our center a couple of years ago. And this paper now has almost 5,000 citations. And a lot of our members know about this paper and did research in PT-symmetry related areas and questions. So with all this said, I am extremely happy to have Professor Bender with us today for our physics colloquium of IBS at Daejeon. And I very much want you now to start your lecture. So the floor is all yours, please, Professor Bender. And we should give him a hearty welcome if things are ready.
Okay, thank you very much. So these are some acknowledgements. So thank you very much for the invitation to speak. And although I must say I much prefer to speak live to a real live audience where I can look at people and see what they're thinking about, rather than just sitting at my desk here. Maybe if I'm lucky, maybe I can visit you sometime and actually meet you in person. It would be a lot of fun to do that. So here's a 30-second summary of my talk. I think the most important thing to measure in physics is energy. And when you measure it, you should get a real number, because that's the only thing we can get when we make a measurement. And if you want the energy to be real in quantum mechanics, you have to assume that the Hamiltonian is Hermitian. At least that's what we learn in elementary courses in quantum mechanics. But it turns out, and that's what I'm going to talk about today, that there's another less mathematical and more physical possibility, and that is that H is PT-symmetric. And I say it's less mathematical and more physical because when you say that the Hamiltonian is Hermitian, you mean that if you write the Hamiltonian as a matrix, then the Hamiltonian is invariant if you take its complex conjugate and its matrix transpose. And that's a very complicated mathematical requirement. It doesn't sound like physics, but when you say PT-symmetry, you mean P is the operation of spatial reflection and T is the operation of time reversal. And those are very physical and very simple and easy to understand operations. Okay, so to begin, remember that Newton discovered gravity. Here is Newton discovering gravity. Okay, but Einstein rediscovered it. And here Einstein is discovering that time is actually money. Okay. And Einstein told us that we should study the Lorentz group, which is maybe the most important symmetry group in all of physics. This is the set of all real 4x4 matrices that map the space-time point x, y, z, and t into x prime, y prime, z prime, t prime. Okay. And these matrices, when they map this space-time point into this space-time point, they have to preserve this light cone quantity, x squared plus y squared plus z squared minus t squared. Okay, that's the definition of the Lorentz group. And of course, parity, which is space reflection, P, and time reversal, T, are all elements of the homogeneous Lorentz group. Okay, so this is because parity changes the sign of x, y, and z. Time reversal changes the sign of t, but because everything here is squared, it's obviously these are obviously elements of the Lorentz group. Okay, now the homogeneous Lorentz group is very interesting. It's a continuous group, but it consists of 4 disconnected parts. Okay, the most important part is the proper orthochronous Lorentz group. Okay, and these are all of the elements of the Lorentz group that are connected to the identity. So this is a subgroup. This contains the identity element. Okay, these are all the elements of this subgroup multiplied by t. And this is all of the elements of this subgroup multiplied by p. And this is all the elements of this subgroup multiplied by pt. Okay, now what we can do is extend the real Lorentz group, which is all real 4x4 matrices, to the complex Lorentz group. So you just allow those matrices to have complex matrix elements, okay? And now what you find is that instead of 4 disconnected parts, the Lorentz group only has 2 disconnected parts, okay? That is, there is a continuous path through the complex Lorentz group from these elements to these elements. And there is also a continuous path from these elements to these elements. Now we know that the world is not invariant under time reversal. We know that. And we know that the world is not invariant under space reflection. Okay. But in fact, what we're going to argue is that we can construct quantum systems that are invariant under P times T, where you change the sign of X, Y, Z, and T. Okay, and that's what we're going to be talking about today. So the theme of this talk is that mathematicians find it enlightening to extend the real number system to the complex number system. And that's because it helps us to understand the real number system better. But in this talk, we're going to extend conventional real physics, just as I did just now, where I was talking about the real Lorentz group, to complex physics, where I was talking about the complex Lorentz group. And when we do this, we can understand all sorts of things much better. We can understand quantization better. We can understand the divergence of perturbation theory. We can generate new kinds of PT-symmetric quantum theories. We can tame instabilities and much, much more. But this is a long, long story, and I'm not going to take all that time. So we'll just mention these 4 things in this talk. Now, this talk is organized in 3 parts. These are the 3 parts of my talk. There's a beginning, a middle, and an end. Okay? So you know that the real world is described by real numbers. For example, we use real numbers to talk about election results. We talk about your IQ is a real number. We use real numbers to describe money. Okay? For example, this is a real quantity of money in Brazil. Okay? But complex mathematics is very powerful, and I just want to take a few minutes to emphasize that fact. For example, complex mathematics explains the convergence of real Taylor series. Complex mathematics can be used to understand the asymptotic behavior of real integrals. Complex mathematics allows us to sum divergent series. It explains real functions, the structure of real functions such as the square root function, and much, much more. But we'll talk about that some other time. Okay, so for example, why do Taylor series stop converging? Okay, so here is the function 1 over 1 plus x to the 4. And if you plot the function, it's nice and smooth. There's no singularity that you can see at all considered as a real function. And yet, if you expand this into a Taylor series, you see that the Taylor series stops converging as soon as the absolute value of x is bigger than 1. Why is this? Nothing happens to the function at 1. Why does the Taylor series stop converging? And as you know, the answer is that there are singularities of this function, but these singularities are in the complex plane. And if you don't know that much about the complex plane, here are some examples of complex planes, okay? If I ever come and visit you in Korea, I would take one of these planes here, maybe this one over here. This is a very, very nice plane. The only problem with this plane is that all the people are sitting over here, but the toilets are over here. Okay, so what about asymptotic expansion of integrals? Here is a real integral, okay? You can't evaluate this integral in closed form, but you can ask, how does this integral behave for large positive x? Okay, how does the integral behave for large positive x? And you might argue, if you only knew real variables, you might argue, look, if x gets extremely big, then this function here, e to the minus 4x t squared, becomes very, very small. Okay, it becomes infinitesimal when x is very big, except it's 0. And therefore, the principal contribution to this integral when x is large must occur at t equals 0. Otherwise, this integral vanishes, okay? If you were to argue that, you would be completely wrong. Completely wrong. Okay? In fact, this is a very subtle integral, and if you could tell me the asymptotic, here's the answer, by the way. This is the asymptotic behavior of the integral for real x as x goes to infinity. It's very simple, but if you could derive this result without using complex variable theory, I think you should publish it. Okay, because in order to solve the problem, you have to use the method of steepest descents, because the contribution is not localized at t equals 0. In fact, what you have to do is you have to take the original contour, which goes from -1 to 1, -1 to 1, and you have to deform it so that it goes from -1 to infinity, and then from infinity back across the imaginary axis and out to infinity again, and then back to 1. You have to deform it into this path because this is called a steepest descent path, okay? And the contribution to the integral is not localized at the origin, it is actually localized in the complex plane at the point I. And if you never heard of I before, even though the answer to this problem is real and the integral is real, if you can derive it without using the concept of a complex number, you're very, very smart, and you might consider publishing your argument. Okay, so here are some divergent series. These are all these series diverge. I don't know if you know what they add up to here, but I will show you the answer. All these series add up to this. That's the sum of those divergent series. If you only heard of real variables, you could sum these series using real variable techniques. But these series are much harder. And to sum them, you need to use complex variable techniques. And these are very important because these are modal sums. For example, if you wanted to calculate the Casimir force in quantum theory, you need to evaluate sums like these, and you must use complex variable theory. You cannot get these results using real variable theory alone. Okay. Complex variables also help us to understand real functions. An example of a real function is the square root function, and the square root function is very confusing because there are two answers, two right here, two answers, okay? The square root of 4 is either +2 or it's -2, okay? Why is that? Well, using real variables to explain this is impossible because you have to extend the real number system to the complex number system, and then you can understand that the square root function is defined on a Riemann surface. What is a Riemann surface? Riemann surface is several complex planes cut and glued together. So here we have two complex planes. If you go around, this is the origin over here. If you go around in the complex plane, you suddenly go on to the other complex plane. And then if you continue around on the other complex plane, you come back onto the first complex plane. Why are there two planes? Because if you take the square root of a number, there are two possible answers. Okay, so this Riemann surface consisting of two complex planes is like a Mobius strip. If you go around 2 times, you return back to the starting point. Okay, so there are lots of things, by the way, that if you go around twice, they return back to their original configuration. For example, this is a Mobius strip stake. Okay, if you go around twice, it comes back to the original configuration. But in physics, there's something else. There's an electron. If you walk around an electron 360 degrees, it's not the same electron. It's different. But if you walk around again 360 degrees, that is 720 degrees, then it looks the same. Okay? Which is very interesting. Okay, so of course you know that complex numbers already appear in modern physics. They appear in the Heisenberg algebra. Xp minus px is not real, it is pure imaginary. It's proportional to I. And there's also an I right over here in the Schrödinger equation. Okay, just look at the Schrödinger equation. Don't look at anything else. Okay. And in fact, it was Wigner who explained to us that time reversal corresponds to complex conjugation, which is a deeply fundamental operation in mathematics, changing the sign of I. That's a deep mathematical symmetry. And when you can convert that into physics, it becomes time reversal. Okay, now, if you take an elementary course in quantum mechanics, you learn that a particle in a potential well has quantized energy levels. Okay, that's what they tell you in an elementary course. And you also learn that going from one quantum level to another quantum level is a discrete operation. It corresponds to a quantum leap, right? You go from one energy level to another one, okay? However, complex analysis gives us a much deeper understanding of quantization. So to give you an example, let's imagine just a two-state system where the states are not interacting. The energies, let's say, are A and B. How do you describe this system? Well, this is the Hamiltonian. Okay, so this is a two-state non-interacting system. But now let's allow those states to interact. So we will couple them with a coupling constant G. Okay, now what are the energies of this coupled system? Well, the energies are obtained by taking the determinant of the Hamiltonian minus I times E. And if you expand the determinant, you get the secular equation. And if you solve this quadratic equation, you find the two energies, and you notice that there is a square root here. There's a square root, okay? And you notice that this square root has singularities. This square root has to be defined on a complex Riemann surface in the complex coupling constant plane, that is the complex G plane. And there are singularities where the square root changes sign, and these singularities are points in the complex G plane. These are the locations of those points. Okay? So the complex two-sheeted Riemann surface corresponding to those energies looks like this. Here is one singularity. Here's the other singularity. Okay? And notice that, in fact, there is not a discrete quantum leap from this energy corresponding to the plus sign to this energy. In fact, you can go from this energy to this energy smoothly, okay? All you do is you smoothly vary the coupling constant in the complex coupling constant plane and go around here, and now you're at the other energy level. So what you see is that on this complex Riemann surface, the energy levels are not discrete. And what you see is that quantization is topological. Why does a Hamiltonian have different energy levels? Because the Hamiltonian is defined on a Riemann surface having discrete sheets in it, and the discrete energy levels correspond exactly to the discrete sheets in a Riemann surface. Okay? Furthermore, these square root singularities here explain the divergence of perturbation series. If you solve this problem using a perturbation series, it diverges at these points. These are the singular points in the complex coupling constant plane that make perturbation theory diverge. And in fact, you can sum this divergent series using complex variable techniques. So you can sum the divergent series and get a finite, physically correct answer. Okay. In fact, for a more complicated problem, why does a Hamiltonian have many different energy levels? You can think of this Riemann surface as the sheets, as the levels of a parking garage. If you want to go from this energy level to this energy level to this energy level, you simply go around and around in the complex coupling plane. smoothly going from one energy level to the next, and so on. Okay? Now, he can't understand this, but you can. It's not very difficult. Okay? So unlike what is taught in conventional quantum theory courses, energy levels smoothly deform into one another under analytic continuation. Energy levels are not discrete, independent objects. There is really only one object, which is a complex energy function. And to get each energy level, all you have to do is analytic continuation. Okay? Now, in fact, you might think this is just mathematics, but it isn't. Because in fact, as you can see in this paper, this is a 2012 paper, this is a beautiful piece of work where they were able to go around the singularities and to go from one energy level to the next energy level in a microwave billiard, okay, in a microwave cavity, okay? And in fact, these are more recent papers in Nature where they were able to actually carry out this analytic continuation smoothly and continuously and go from one sheet in the Riemann surface to the next. These are absolutely beautiful pieces of work. But I do want you to notice something very nice. You notice in the title of this paper, you notice the words PT-symmetry. Okay, and so what we're going to talk about here in this colloquium is the meaning of PT-symmetry. Okay, and what you're going to see is that PT-symmetric quantum mechanics consists of extending quantum mechanics into the complex domain. And what you're going to see is that if you respect PT-symmetry, the eigenvalues can remain real, just as if you had a Hermitian Hamiltonian, and unitarity can be preserved even if the Hamiltonian is not Hermitian, which is really interesting. Okay, and I want you to remember, of course, that a PT reflection is a simultaneous reflection of space and time. This picture is on the cover of a recent book on PT-symmetry. Here's the book. You might enjoy reading it, and there's the cover with the picture on it. Okay, so here is an early example of a PT-symmetric Hamiltonian. Here it is. Okay, this Hamiltonian is obviously not Hermitian because there's an I in it. This is a Hamiltonian that has been extended into the complex plane, but this is a PT-symmetric Hamiltonian. Why? Because under parity, X changes sign. And you remember I told you that under time reversal, I changes sign. So this Hamiltonian is PT invariant, even though it is not Hermitian. Okay. Now, when this is a Hamiltonian that a number of different people have studied. This Hamiltonian comes up as a one-dimensional model of the Liang edge singularity. It comes up in Region field theory. But I must say, the first time I saw this Hamiltonian, because I only had an elementary course in quantum mechanics, I said, the way I see it, this theory is crazy. It's completely crazy because this is not a Hermitian Hamiltonian. However, that is just one element of an infinite class of Hamiltonians, which is this, okay? So what I'm doing here is I start with the harmonic oscillator, which is p squared plus x squared, okay? And I am multiplying x squared by I times x to any real power, which we'll call epsilon here, okay? And this is a PT-symmetric Hamiltonian. Why? Because under parity, X changes sign, and under time reversal, I changes sign. So although this Hamiltonian is not Hermitian, it is PT-symmetric. It is only Hermitian if epsilon equals 0. But if you make a plot of the eigenvalues, here they are. As a function of epsilon, by the way, this Hamiltonian I just showed you on the previous transparency, p squared plus ix cubed, that just corresponds to epsilon equals 1. And here are the eigenvalues of that Hamiltonian, and you can see they are all real. Okay? And in fact, for all epsilon, for all real positive epsilon, these are the eigenvalues, and you can see the eigenvalues are all real and positive and discrete. And this is a really strange result. If you haven't seen this before, it's very strange, because at epsilon equals 2, we are talking about the Hamiltonian p squared minus x to the 4. And this is an upside down Hamiltonian, a negative potential, and yet the eigenvalues are all real and positive and discrete. Okay? And if you don't believe it, you can read a proof. The proof, in fact, is very difficult, very long, very detailed, okay? But you can read it. And this is a complete proof, a rigorous proof of the reality of the eigenvalues for positive epsilon, for any positive value of epsilon. Okay, so this talk is about PT-symmetry, and what I have told you, I want to emphasize this, that PT-symmetric Hamiltonians are complex deformations of Hermitian Hamiltonians. That is, you begin with a Hermitian Hamiltonian and you introduce a deformation parameter epsilon, and that is what I'm doing over here. You notice I take the Hermitian Hamiltonian, the harmonic oscillator Hamiltonian, p squared plus x squared, but I deform it by multiplying by ix to the epsilon. Okay, so I deform the Hermitian Hamiltonian into the complex plane. So here's a very simple example. Let's take the harmonic oscillator and add on I epsilon x. Okay, and any first year undergraduate student can calculate the eigenvalues of this Hamiltonian. Okay, all you need is an elementary quantum mechanics course. There's the Schrödinger equation. There's the boundary condition. Here are the eigenvalues. And you notice that although this Hamiltonian is not Hermitian, the eigenvalues are all real and positive and discrete. Okay. And in fact, this picture is a generic picture. We don't have to begin with the harmonic oscillator. We can begin with the anharmonic oscillator, which is p squared plus x to the 4, multiplied by ix to the epsilon. And again, here are all the energy levels, and you see they're real and positive and discrete. Okay, here's another one. Let's take p to the 4 plus x squared and multiply by ix to the epsilon. And again, the eigenvalues are all real and positive and discrete. And here's a really fancy one. Let's take the harmonic oscillator p squared plus x squared and multiply by ix to the epsilon. And just for fun, we'll throw in log of ix. And once again, the eigenvalues are all real and positive and discrete. Okay, so if you find this interesting, but you don't like equations, you can read about this. This is a short 3-page popular physics paper in Europhysics News. They asked me to write a summary of the idea of PT-symmetry. Okay, this is 4 years ago in 2016. Okay, and you can read about it. And in fact, in the paper, you'll see this picture. This is a picture of something that was tremendously exciting to me. This is the first time in my life this ever happened, because I'm a mathematical physicist. I never thought that anything I ever did would have some kind of could be tested in the laboratory. But in fact, I got the most exciting email I ever got was an email saying they have now built the first physical device to actually look at a PT-symmetric system. It was a PT-symmetric optical system. This is a laboratory in the United States, in the University of Arkansas. And this is the experiment, a very simple tabletop experiment, okay, where they were able to observe a PT-symmetric system right there. And this has become a very popular area of research. In fact, I was very happy back in 2015, there was this cartoon in Nature Physics, and it was called The Top 10 Physics Discoveries of the Last 10 Years. Okay, top 10. How about that? Okay, of course, this is a cartoon, so this is funny. And every one of these is a pun. For example, over here is the Higgs boson. Not the Higgs boson, but the Higgs boson. They changed this letter here, O into I. Okay, so there's the Higgs boson. But I was very happy to see that they included parity-time-symmetry in optics. Of course, they made a mistake here. They called it party time. They left off the I. Okay, so they called it parity-time-symmetry in optics. Okay, so there are now over 5,000 papers, published papers on PT-symmetry, which is very exciting. It's very nice. In fact, you can see people doing PT-symmetry all around the world. This is, you can see, here's, I was in China at a conference, and here's an example of PT-symmetry. If you notice, do you see the PT? If you are Chinese and you're used to reading in Chinese, you might not see it. So let me help you. There it is. Okay, you can see PT in China here. Okay, so let me show you why it is that complex variables helps us to understand the nature of PT-symmetric quantum mechanics. Real variable analysis is not strong enough. So let's look at the case of epsilon equals 2. That is the Hamiltonian p squared minus x to the 4. And you remember I showed that to you, and I showed you that its eigenvalues are real and positive. You remember that, okay? So this is the PT-symmetric quartic potential minus x to the 4. And this potential looks unstable on the real axis. It's unstable. How can it have bound states? It looks like a potential that is repulsive. How can it confine physical bound states? Well, we have to use complex variables. Okay, so to explain what is going on, let me take you back to your very first course in undergraduate physics. It's what you took when you were a first-year undergraduate student. Remember what they teach you in introductory classical mechanics. The thing that they study, one of the things they study, is the classical harmonic oscillator. And all you learn is that this harmonic oscillator describes back and forth motion on the real axis. Okay, so what happens is the particle goes all the way out, given the amount of energy it has. It goes all the way out. It stops, it turns around and goes back, and then it stops, and it turns around and goes back, and it goes back and forth. Between these turning points, where are the turning points? Well, given the energy E for the Hamiltonian, when it stops, P is equal to 0, so E is equal to x squared, and that tells us that x is plus or minus the square root of E. So these turning points are located at plus or minus the square root of E. Okay, and what you learn, by the way, is that this is the classically allowed region, because this is where the classical particle is oscillating. And over here, past the turning point, and over here, these are the classically forbidden regions, because the classical particle cannot go there. Okay, that's what you learn. Okay, so in case you have trouble understanding that, this is an example of a classically allowed and the classically forbidden region. Okay, Okay, so by the way, you can ask, why is it that the classical particle cannot go over here? Because if the particle is over here, then E, remember E is equal to x squared at this point? So x is bigger than the square root of E. So x squared is bigger than E. But if x squared is bigger than E, then p squared is negative. How can p squared be a negative number? You would think that's impossible. That's why this is a classically forbidden region. However, that's not true. If we put a particle over here where p squared is negative, that means that the momentum of the particle is imaginary. And that means that a particle over here travels off the real axis into the complex plane. And what it does is actually travel in an ellipse. So the particle goes off the real axis into the complex plane, around an ellipse, and back to here. And it goes around and around and around. And in fact, this is very useful. Complex variables is very useful here because we realize now that the thing that you learned in elementary physics, this back and forth motion between the turning points, is just a degenerate ellipse. That's all. Okay. By the way, however, this elliptical orbit is not a Keplerian orbit. It's not Keplerian because if you have Keplerian orbit, our planets are traveling in a Keplerian orbit, and the sun is at one of these foci of the ellipse. This is not just a turning point, but it's the focus of the ellipse. Okay. But for planetary orbits, the distant planets like Jupiter and Pluto have a very long year. They take very long to go around the sun, whereas the inner planets go around the sun very quickly. But these orbits are different. These are not Keplerian because every orbit has exactly the same period. And to prove that is very easy, it's very trivial. It's just a consequence of Cauchy's theorem for complex variables. That's all. Okay? Now, what happens if we try to make this a little more complicated? Instead of the harmonic oscillator, let's increase epsilon to 1. And now we have the cubic PT-symmetric Hamiltonian, and these orbits deform into the complex plane. They are no longer ellipses, but they are still closed orbits. There are now 3 turning points, here, here, and here. If you start at this turning point, the particle goes back and forth between the turning points, just as before. Just exactly as before, except it's going back and forth in the complex plane. Okay? And other orbits go around the back and forth orbit, and they enclose the back and forth orbit, just as before, just as in the case of the harmonic oscillator. Okay? Now, what happens if we increase epsilon to 2? Now we have these turning points down here, and also 2 more turning points up here. If you start a particle at the turning points, it goes back and forth between the turning points. Okay, that's like classical, real classical motion. But other orbits are also closed, and they have exactly the same period, and so they fill the complex plane. They completely cover the complex plane. Now, here is the point. Suppose we start a particle at the origin and we give it a slight push. It runs off to infinity. Where does it go next? Okay, that's a really interesting question, okay, which we can't answer using real variables. In fact, if you do the calculation, you find that if you start a particle right here at the origin, and you have this particle balanced on top of an upside down potential, this particle rolls off to infinity, and it gets to infinity in finite time, t. So the question is, where is the particle at t plus 1? And real variables doesn't tell us the answer, but complex variables does, because all we have to do is allow one of these we allow these orbits to get bigger and bigger and bigger and approach the real axis. And what we see is that a particle beginning at the origin rolls off to infinity. It then goes infinitely fast, like this, all the way around to minus infinity. Okay, and then it rolls all the way back up to the origin. Okay, and it does so in the same amount of time that it takes for the particle to go back and forth between the turning points. The period of every orbit is the same. So what happens is, although the particle is statically unstable at zero, what we see is that if you give the particle a push, it comes right back to zero. And then it keeps going. It comes right back to zero again and again. Okay? So if you ask, suppose we ask, what is the probability density for a classical particle? We're still talking about classical mechanics here. What is the probability for a classical particle in this upside down potential to be found on the real axis at the point X? What is the probability? Well, because the particle is moving very, very fast out here, it's very unlikely to be found here, but it's most probable that you will find the particle right near the origin. So the probability density is biggest at the origin and very small, zero, at infinity. So we see that the particle is localized at the origin. So even though we have an unstable potential, it is most likely to find the particle at the top of the hill, at the origin. In fact, what is happening here is the probability is very large to find the particle at the origin. And then the particle whizzes around in the complex plane and comes right back to the origin, where it's very likely to be found. So even though the particle is statically unstable at the origin, it is dynamically stable in the complex plane. And you know lots of examples like this. A bicycle is an example of something that is statically unstable, but dynamically stable. A moving bicycle doesn't fall down, okay? Or a top. Of course, if the top is not rotating, it falls down. So it's statically unstable. Okay. Now,
Professor Bender,
yeah.
Can I ask something? So is this probability dropping exponentially or as a power law or?
Actually, in the case of the quantum mechanical theory, it drops exponentially.
Mm-hmm. But you here you were referring to the classical system.
That's right. That's right. So now I'm going to talk about the quantum system, and in fact, it's very simple. The quantum system, how do you calculate the approximate energy levels of a quantum system? And the answer is, you just do WKB, right? You take the integral of p dx, you set this equal to n plus a half pi, okay? And that gives you the energy levels. And if you do this simple calculation, you will find these energy levels that I showed you right over here, right here. Okay, so at epsilon equals 2, with a minus x to the 4 potential, here are the energy levels. And if you just do that simple calculation, you will get the energy levels accurate to a tiny fraction of 1%. WKB is very, very accurate, okay? Which is very nice. Okay, so what you see is that the instability, the static instability at x equals 0 is tamed, and it has now become, the system is dynamically stable. So complex analysis is fantastic because it allows us to tame instabilities. Lots of systems that you thought might have been unstable are not unstable. And physical systems that seem to be unstable might become stable in the complex domain, which is really interesting, okay? Why is it that the instability goes away? There's a very simple answer. you know, when you say a quantum system is unstable, what you mean is that its energy levels are unbounded below. Did you hear those words? Unbounded below. Those words involved an inequality. The word below means less than. Okay, it involves an inequality, but you have to remember that when you extend the real numbers to the complex numbers, everything about the complex numbers is the same as for the real numbers, except for one thing. Complex numbers do not have an ordering property. You can't say that one complex number is bigger than another complex number. So you can no longer say less than or greater than when you're talking about complex numbers. And that's the reason, that's the deep reason why physical systems that look unstable on the real axis may not be unstable at all. They may actually be stable in the complex domain. Okay, so we lose the notion of inequality. There's no inequality. Okay? However, it is not always true that a PT-symmetric theory has real eigenvalues. It might not always be true. And this, I'm just showing you this picture that I showed you before again. And I want you to notice what happens. When epsilon is positive, all the eigenvalues are real and positive. But when epsilon is negative, something interesting is happening. This energy level and this energy level, as epsilon goes below 0, come together. They become degenerate at this point, and then they seem to disappear. And the same is true of the next two energy levels and the next two and the next two and so on. They have disappeared. Well, they haven't really disappeared. What has happened is that the energy levels have become complex. Okay? So you notice that when epsilon is less than 0, the energy levels are complex. But when epsilon is greater than 0, the energy levels are real. And there's a transition at 0. And we call this the PT boundary. Okay? So this is the region. Yes?
Sorry to interrupt. Just to clarify one point for me, maybe also for others. So let's say you take epsilon equals 2. So you have Hamiltonian p squared minus x to the 4.
Right.
And then you look at eigenstate, you solve the Schrödinger equation, and you look for eigenstates with, I guess, with some specific boundary conditions, isn't it? And
that's the key point.
So,
And in fact, this is this is a wonderful question. Okay, could I ask you a favor? At the end of my talk, please ask the question again, because I will give you a complete explanation to it.
Thank you. Okay.
But I'm afraid if I take 5 minutes to answer the question, I may not have enough time left to finish.
Thank you.
Okay, but yes, indeed, it has to do with the boundary condition. But don't forget to ask me the question, because that's a really great question. So we call this the region of unbroken PT symmetry, where the eigenvalues are all real, and the Hamiltonian behaves just like an ordinary Hermitian quantum mechanical Hamiltonian. And over here, the eigenvalues are complex. So it does not behave like a Hermitian Hamiltonian. And we call this the region of broken PT symmetry. And this is a phase transition between this region and this region. And you notice that the phase transition occurs at epsilon equals 0. And you notice that epsilon equals 0, that is the harmonic oscillator. So you notice that Hermitian Hamiltonians live at the phase transition between PT unbroken regions and PT broken regions. In fact, that is the role of Hermitian Hamiltonians. There are infinitely many more PT-symmetric Hamiltonians than Hermitian Hamiltonians, but the Hermitian Hamiltonians sit at the boundary between unbroken and broken regions of PT symmetry, where the eigenvalues are real or complex. So this is a summary here. PT symmetry does not conflict with conventional quantum theory.
Sorry?
Yeah.
Can you go one slide before?
Yeah.
but as far as I understand, I mean, the PT symmetry is there for any values of epsilon, right? So how can I?
Absolutely.
So
Absolutely.
how can I mean, is there any, let's say, first principle way to distinguish the so what do you mean by broken PT symmetry, and how can I distinguish it?
Yes. So that's a wonderful question. Okay. And in fact, the answer is extremely difficult.
Okay.
Okay. This is not a simple question. You cannot look at a Hamiltonian and say, this is the unbroken region and this is the broken region. You can't do that.
And also, if you want a related
fact,
question,
it's very, very hard. It's very, very hard to answer that question for any given Hamiltonian. You have to work. You actually have to calculate the eigenvalues and see where they are real and where they are complex.
Okay. And also, if I can, related question, I mean, also, let's say at epsilon equal to 2, my Hamiltonian is Hermitian, right? So how can I distinguish that epsilon equal to 0 is at the boundary?
Yes. So I'm going to answer that question at the end of my talk, if you don't mind. Okay. Because
thank you very much.
That's really, really interesting question. The short answer to your question is, if you look at a Hamiltonian, you have no idea what the eigenvalues are.
Okay.
Not until you understand the boundary conditions. So a given Hamiltonian can have many different spectra depending on the boundary conditions. Don't use your intuition about the real axis, because it can lead you down all kinds of wrong conclusions.
Okay, thank you.
Okay, this is a really interesting and non-trivial question. So, but I give you my word of honor. I promise to answer you after my talk. Okay. So, but this is what you should remember. For PT, symmetry doesn't conflict with conventional quantum theory, but the condition of PT symmetry is weaker than Hermiticity. So all the eigenvalues of a Hermitian Hamiltonian have to be real. For PT-symmetric Hamiltonians, only the secular equation is real. And the solution for the eigenvalues, the solution to this equation, the eigenvalues could be all real or they could be complex. So there are two possibilities. PT-symmetric theories can have an all real or a partly real spectrum. And I'm going to explain now what that PT transition is. Okay? But you should remember that you can have broken PT or unbroken PT. Okay? So Hermitian Hamiltonians, remember, are boring. And that's because the eigenvalues are always real. Nothing interesting happens. Okay? He's one of our presidents. He is really boring. Do you know who that is? It's his daughter. Okay. However, PT-symmetric Hamiltonians are astonishing because there's a transition between parametric regions of broken and unbroken PT symmetry, and this is very easy to observe experimentally. Okay? So I want to explain to you intuitively what is going on at the PT transition. Here's an example of a PT transition. This is P, Putin. This is T, Trump. Okay, and this is a transition. Okay? So this is actually very simple sounding. Okay? I want you to imagine a closed box over here, and something is flowing into the box. So we say this box has gain. It doesn't matter what's flowing into the box. It could be energy. It could be just water. It doesn't matter. It could be electrons. But something is going into this box. If you were to write down the Hamiltonian for this system, it is a one-dimensional matrix of the form A plus IB. And the reason why this is complex is because stuff is going into the box. In fact, if B has one sign, stuff is going into the box. And if B has the opposite sign, it is like radioactive decay and stuff is going out of the box. Okay, so the box is either increasing or decreasing in time. Okay, now here are two boxes. This box has gain and this box has loss. Stuff is going into this box and stuff is going out of this box. Now the boxes are not interacting. The boxes are not interacting, but the Hamiltonian for this system is a 2x2 Hamiltonian, okay? It's A plus IB and A minus IB because stuff is going in and stuff is going out, okay? Now this system is not in equilibrium, but this is an example of a PT-symmetric system. Why? Because under parity, what you do is you interchange the two boxes. You interchange the two boxes. So this box goes over here and this box goes over there. And under time reversal, gain becomes loss and loss becomes gain. So this is a PT-symmetric system. But you notice that the eigenvalues of this PT-symmetric system are complex. These are the eigenvalues. They're complex numbers. And that's because the system is not in equilibrium. Okay, so what I'm going to do is I'm going to connect the boxes with a pipe. So stuff is flowing into this box. It's flowing out of this box. But now the system, if this pipe is thick enough, the stuff in this system can flow into this system and then flow out. Okay, so now the system can be in dynamical equilibrium. Okay, and if the coupling constant is G, if G is big enough, the eigenvalues can be real. Okay, now this system is PT-symmetric. T, time reversal, consists of complex conjugation. Parity P is this sigma 1 matrix, okay? And if you can go home and do the calculation, you will see that PT commutes with this Hamiltonian, okay? And now, if you find the eigenvalues of the Hamiltonian, you write down the secular equation. It's real, as I said. Here are the eigenvalues, and you notice that if G is big enough, if G is bigger than B, then the eigenvalues are real. Okay, and this is a simple demonstration. So there is a PT transition where the eigenvalues go from being real to being complex, and this transition occurs when G is equal to B. Okay, so you can have a system with complex eigenvalues and real eigenvalues, and these eigenvalues become real as soon as the system goes into dynamic equilibrium. Okay, and that is the PT phase transition. So what I want you to remember is that PT-symmetric systems are really interesting because if they have real eigenvalues, they look like a Hermitian Hamiltonian describing a closed quantum system. They behave just like a Hamiltonian that is Hermitian. But if the eigenvalues are complex, then they behave like a non-Hermitian Hamiltonian that is describing a scattering system. So PT-symmetric Hamiltonians are situated right between Hermitian and non-Hermitian Hamiltonians. This guy is obviously very happy about PT symmetry, and so am I. I'll show you my shirt here. That's my t-shirt, okay? It's good to stand up instead of continuing to sit at my desk. So just to give you, just before I stop my talk, I'll just mention that there are lots and lots of theoretical applications of PT-symmetric systems. If you know something about quantum field theory, you may know that when you renormalize a quantum field theory, the resulting Hamiltonian becomes non-Hermitian. And people talk about ghosts. But in fact, it very often turns out that that Hamiltonian, although it is no longer Hermitian, is PT-symmetric. And as a PT-symmetric system, there are no ghosts. That's not true that there are ghosts, and the eigenvalues continue to be real, okay? And there are lots of experimental studies of PT symmetry. And before I quit, I'm just going to show you some pictures. These are some of the experimental studies that you can read about. these are wonderful experiments. The picture I showed you of an optical experiment was published in Physical Review Letters back in 2009. That is the first optical experiment involving a PT-symmetric system. This is a much better experiment. It was published in 2010. It's an absolutely beautiful experiment. It was published in Nature. This is an experiment on PT-symmetric diffusion, atomic diffusion, that was done in Shanghai and Rutgers. This is an experiment on PT-symmetric optics done at Caltech in the United States. This is an experiment involving superconducting PT-symmetric superconducting wires. This is published in Physical Review Letters. This is done in Indiana. This is an experiment on PT-symmetric PT-symmetry breaking in a microwave billiard, and I talked about this experiment previously. Okay, this is an experiment on PT-symmetry breaking and lasers. Okay, so these are PT-symmetric lasers. These are PT-symmetric photonic lattices, PT-symmetric exceptional points in lasers, PT-symmetric photonic lattices, superconductivity, which was done at Argonne National Laboratory in the United States. This is an experiment done on PT-symmetric NMR in Beijing. This is PT-symmetric metasurfaces, okay, done in Texas. This is PT-symmetric photonic crystals done in California at Stanford. This is an experiment on, this is an absolutely beautiful, beautiful, beautiful experiment done at Stanford involving power transfer. If you're interested in this, I'll tell you about it after my talk is over. It's really, really interesting, and it may have lots of practical applications, modern applications. This is a very beautiful experiment on a PT-symmetric electrical circuit. This is an oscillator coupled to another oscillator. Okay, remember the box with gain and the box with loss? Well, these, remember, and the pipe between them? Well, these are two electric circuits that are coupled inductively. Okay, and you can put power into one circuit inductively and take it out of the other circuit using a resistor, and now you have a PT-symmetric system, and you can study it and look at the PT phase transition. Okay, and when I saw this experiment, I said, wow, maybe I can do an experiment, even though I'm a theoretician, and I did this experiment. This is an experiment on a PT-symmetric mechanical system, two pendula swinging back and forth, and they're coupled because they're hanging from a string, the same string. And this pendulum is slowed down by an electromagnet, and this pendulum is speeded up with another electromagnet. So we have a system with loss and gain, and they're coupled. And there it is. Now we have a PT-symmetric system, and we can study the PT-symmetric symmetry breaking in this system very easily. Okay, and this is the equation for the coupled pendula. Okay, pendulum with loss, pendulum with gain, and they're coupled. Okay, and here is a really fancy experiment. These are two coupled whispering gallery microcavities, which I was lucky enough to participate in. You can have, this is called a whispering gallery. You can have a light beam going around and around and around in this microcavity. This is a tiny microchip, just 30 microns across, okay? A light beam can go around 1 million times before it's absorbed. And you can shine a laser on this to pump energy in. And because there's always a natural loss in a cavity, there is loss here, there is gain here, and they're coupled. Remember, there's a box with gain, a box with loss, and they're coupled. Okay? Okay, so here is an overview of my talk. I hope you found it interesting. Well, I hope this is not you over here. Okay, I hope you're really interested in this stuff. Thank you for listening. I hope you, as I say, I hope you found this stuff interesting, and I'm very, very happy to answer questions.
Thank you, Professor Bender. So let us first thank our speaker. Thank you for a really wonderful talk. So now we have time for questions, and I see a raised hand. Juzar, please unmute yourself. And
well, would you like me to answer the question that you asked me before, or do you have? If you have a different question, I'm happy to answer that as well.
Okay. Well, first, perhaps. Okay. Let us go to that questions.
Whatever. Whatever you like.
Well, I would suggest let's okay, since let's talk about boundary conditions then again.
Okay, so what you were asking me about is what you said was, I have this okay, maybe I will, okay, can you see this okay?
Yes.
Okay, so you were asking me about this upside down potential, minus x to the 4 potential, and what you were saying was, how could it be
that...
I
didn't ask how. No, I just asked, what are the boundary conditions you impose in order to end up with the statement that there are only positive eigenenergies and they are discrete and real?
Right.
Real and fine, we are all fine, but we know that there are lots of there's a hell of a continuum there, but of course all the wave functions probably don't satisfy your boundary conditions.
That's right. That's right. Exactly right.
So the funny thing is you have...
So let me answer the question, first of all, by showing you something very funny. I suggest that you never ask, this is a very hard question about a very simple looking thing. You should never ask, if you're giving an exam to your students, don't ask the following question, okay? So you might say in an elementary quantum mechanics course, suppose we have the Hamiltonian for the harmonic oscillator, which is this Hamiltonian, okay? And you might ask your students, look, we know what the eigenvalues of this Hamiltonian are. I mean, this is the first thing you learn in quantum mechanics, and you can see that the eigenvalues of this Hamiltonian are whoops, are 2n plus 1 times epsilon. Okay, everybody knows this. And of course, n here is 0, 1, 2, 3. Okay, everybody knows that these are the eigenvalues of the harmonic oscillator. Omega is just a parameter. Okay, you could call it a mass parameter if you want, or it doesn't matter. Or you can call it a frequency. It doesn't matter. But those are the eigenvalues of the harmonic oscillator. Now, here's the question you shouldn't ask your class. You can say, look, what happens if I go into the complex omega plane? So here is the complex omega plane. And what I'm going to do is start with a positive value of omega over here, and I'm going to continue to a negative value of omega. Mm-hmm. Now, if I do that, so I replace omega by minus omega, then obviously the Hamiltonian is exactly the same Hamiltonian. because there's an omega squared in that Hamiltonian. But it seems as if the eigenvalues are all negative now. So does this mean that the same Hamiltonian has negative eigenvalues as well as positive eigenvalues? This is absolutely crazy. Okay, now this is a very hard question, because what we've done here is, instead of staying on the real axis, which is where we have a lot of intuition and where we understand, or at least we think we understand, what is going on, what we have done is to move omega into the complex omega plane. Okay, we have moved omega from positive values to negative values through the complex plane, and the eigenvalues seem to be negative now. So is it true that the harmonic oscillator has negative eigenvalues? And the answer is yes, it does. But what we have done when we rotated omega was also to rotate the boundary conditions. I never said anything about boundary conditions. So one Hamiltonian can have many different spectra depending on the boundary conditions. So let me explain what I mean. So you know that the eigenvalues of this Hamiltonian are Gaussians times polynomials, and we don't care about the polynomials. The important thing is the Gaussian, okay, because that's what determines the boundary condition. And so the eigenfunctions, the nth eigenfunction psi sub n looks like an exponential of e to the minus omega x squared, okay, over 2. That's the form of the eigenfunction times a polynomial, and the polynomial, as you know, is a Hermite polynomial, but that doesn't matter. But now you can see what is happening here. As we rotate omega from positive values to negative values, you notice that there's instead of a minus sign here, there's a plus sign. And that means that the eigenfunctions are no longer vanishing on the real axis. Okay, in fact, they're vanishing on the imaginary axis. So in fact, there are, for the harmonic oscillator, there are 2 different regions in the complex plane, and I'm going to draw a picture of the complex plane. There's one region so there's the red region, which is where the eigenfunctions vanish if you want to have a positive spectrum. And there's this purple region here, okay, where the eigenfunctions vanish if you want to have a negative spectrum. So one Hamiltonian here can have 2 different spectra. And in fact, in general, a Hamiltonian can have many, many, many different spectrum. It could have dozens of different spectra, depending on how many sectors in the complex plane you have. Okay. Now, in the case of the harmonic oscillator, it's very simple, and there are only this pair of sectors and this pair of sectors, and those are called Stokes sectors. Okay. And in each Stokes sector, you are requiring that the eigenfunctions vanish exponentially fast. Okay. Now, if you ask me about, if you are interested, so now that you understand that, if you are interested in the Hamiltonian that we started out discussing, where is it? Here it is. If you're interested in this Hamiltonian, we have to ask, how did you make that Hamiltonian? Where does that Hamiltonian come from? And I'm going to give you 2 possible ways you could build a Hamiltonian like this, okay? The first way is to start with the Hamiltonian p squared plus g x to the 4. So that's a harmonic oscillator. Let me put in an h. Okay, so I'm going to put in a coupling constant, and what I'm going to do is rotate this coupling constant from positive values to negative values, just as I did with the harmonic oscillator, okay? So that now I end up with this Hamiltonian that we're discussing. But another way to make that Hamiltonian is to rotate the Hamiltonian, is to do this, is to begin with the harmonic oscillator and to multiply it by ix to the epsilon like this, and let epsilon go from 0 up to 2. So in this case, I'm moving epsilon from 0 to 2, and we're going from the harmonic oscillator to this negative potential anharmonic oscillator. And in the other case, we're rotating the coupling constant. If you do that, you get two completely different boundary conditions on the eigenvalues. And the boundary condition that is most commonly understood is a boundary condition. So if you do the first, which is the way most people would make a Hamiltonian with the negative potential, if you do this first, what happens is that the eigenfunctions initially are vanishing. They initially vanish in two Stokes wedges that include the real axis. They vanish exponentially fast, okay? And as you rotate G from positive values to negative values, the resulting picture looks like this. Okay, it looks like this. So the eigenfunctions now continue to vanish exponentially fast in this Stokes wedge and in this Stokes wedge. This Stokes wedge is below the real axis. This is above the real axis, but the Stokes wedges are touching the real axis. So on the real axis, the eigenfunctions are no longer vanishing exponentially fast, as you know, because waves are propagating out to infinity, and the eigenfunctions are only vanishing algebraically, and they're oscillating instead of vanishing. Okay. On the other hand, if you do what I have on this in this picture here, now you begin with the eigenfunctions for the harmonic oscillator, and they're vanishing in Stokes wedges. But after you allow epsilon to go from 0 to 2, the eigenfunctions vanish instead of this picture where they're vanishing exponentially above the real axis on one side and below the real axis on the other side. Now the eigenfunctions vanish exponentially below the axis on this side and below the axis on this side. That's a very big difference, okay? And when you have a situation like this, these two wedges are PT-symmetric relative to one another. And let me explain why. Because remember, under time reversal, let's take a point. Okay, I'm taking a point over here in this wedge. Under time reversal, this point goes into its complex conjugate. So it goes up over here. Okay, it's outside the wedge now. Okay, and then under parity, it is reflected through the origin. It goes into minus itself. So it goes over here. Okay, so under time reversal, it goes into its complex conjugate, and under space reflection, x goes to minus x, so it goes over here. So therefore, this wedge is PT-symmetric. This and this wedge, these two wedges are PT-symmetric relative to one another. So the system, the whole eigenvalue problem is a PT-symmetric eigenvalue problem, which is really interesting, okay? Okay, so what is happening is that the wedges, you start with harmonic oscillator wedges over here, of course. And what happens is that as you increase epsilon, this wedge rotates down, and this wedge rotates down, and you get a completely different physical system. So the same Hamiltonian can describe completely different physics depending on how you construct that Hamiltonian. That is, if you take one path, this path to that Hamiltonian, you get one system, which is the one that you are very familiar with and know from, and you intuitively understand as a system with unbound states traveling, particles traveling through an upside down potential. Okay, it's a scattering problem. And this problem here, which is completely different, this is a bound state problem. And although the potential looks repulsive, it isn't, because it is dynamically stable. This is a remarkable, no one ever imagined such a crazy thing before we started working on PT symmetry. This is very non-intuitive, but in fact, you can do experiments. In fact, there's a very nice experiment that you could do and has not yet been done, but you could observe the energy levels, okay? Just do a scattering where you impose these boundary conditions. And I can tell you about, that's a more complicated discussion, but I could tell you how you could design such an experiment. And I think that would be a prize-winning experiment, because the spectrum that you would discover is precisely this spectrum that I showed you. It's this spectrum back here, this one, okay? You would see this corresponding to epsilon equals 2, you would see these positive eigenvalue bound states. And that would be a macroscopic quantum experiment. And if you do that, I think you deserve a prize, because that experiment has not yet been done. It is a doable experiment. I'm sure it can be done as a tabletop experiment. It's not trivial. But I would absolutely love to see that experiment done. And you would be able to directly measure these bound state energies.
Okay, thank you.
I'm sorry, I gave you a very long answer.
Thank you very much. Thank you very much for this answer. So we see that boundary conditions do matter, and many more things as well. But we are a bit behind our schedule, I fear. So we have now 2 questions. So Juzar was first. Please shoot and ask your question.
Yeah, thanks. Thanks, Prof. Bender, for this talk. So my question is more about the structure of quantum mechanics itself, because somehow while you're discussing PT symmetry, you maintain the structure, meaning you maintain the Schrodinger equation, the Heisenberg equations of motion, so on and so forth. Can you just comment why this is chosen to be so, in the sense that why maintain the structure of quantum mechanics when you're venturing into non-Hermitian Hamiltonians itself?
Oh, I wouldn't dare change the basic idea of quantum mechanics. That is, the notion of a Hamiltonian and the notion of an action principle to derive the equation of motion and so on. All that I am absolutely not changing. All I'm doing is looking at Hamiltonians, specific Hamiltonians that have specific discrete symmetries, in this case, a PT symmetry, but I don't want to change quantum mechanics. What I am saying, actually, there is something that I did not say in the talk because I didn't want to take the time. There are 2 crucial things about quantum mechanics, and we absolutely believe these are very important. The first is that you want the energy levels that you measure I mean, whenever whenever you do a physical experiment, what do you actually measure? You measure an energy. Energy is the most important thing in physics. Okay. I mean, you may think, for example, that you're measuring the position of a particle, but you're not. You're actually measuring an energy, because to find out where a particle is, you have to look at the particle. And when you look at the particle, you scatter photons off the particle. And these photons go into your eyes and they deposit energy in your eye. So the nerve in your eye measures an energy transition. You're depositing real positive energy into your eye, and you are doing an energy measurement. Whenever you measure anything, it's just energy that you measure. So that's fundamental, and we want the energy to be real and positive, okay? But there's a second thing that I didn't really talk about, except in passing, and that is the other fundamental idea of quantum mechanics, which is not something that you think about in classical mechanics, is unitarity. That means the conservation of probability. You can't have things disappearing or suddenly appearing out of nowhere, okay? So probability has to be conserved, and basically all that it means is that if you have an eigenstate, this eigenstate, psi as a function of time, okay, if you measure the norm of this state, which is this, okay, this norm has to be conserved in time. It's a constant in time. You cannot change the norm of a state, okay? And that's called unitarity or conservation of probability, okay? And it's extremely important. I mean, when I say I'm not changing the basic idea of quantum mechanics, maybe even more fundamental, some people would regard it as even more fundamental than positive energies, is the statement that the norm of a state has to be time independent. Okay, we want the norm of a state to be time independent. And will that be true? And the answer to the question, this took us a long time. It took us, I think, much more than a year to understand. But the answer to the question is, if you have a Hamiltonian that is PT-symmetric, okay, what that means is that PT commutes with the Hamiltonian. Okay, so if you have a Hamiltonian that is PT-symmetric, but also if you are in the unbroken region of PT-symmetry, that means if the eigenvalues of this Hamiltonian are all real, like the Hamiltonians I showed you, okay, then this Hamiltonian has a secret symmetry that we didn't know about for more than a year, okay? And this symmetry is represented by a symmetry operator, which I would like to call C. And this Hamiltonian commutes with this symmetry. Okay, so we didn't know that if a Hamiltonian is PT-symmetric and if the eigenvalues are real, then it has what is called C symmetry. C is a Hermitian operator, just like parity, okay, and it commutes with that Hamiltonian. In fact, in simple cases, I can give you the exact representation of C, but in more complicated cases, I can't. So it turns out for the Hamiltonian, H equals P squared minus X to the 4, for P squared minus X to the 4, I can calculate C exactly. But for the Hamiltonian, H equals P squared plus IX cubed, this Hamiltonian, okay, I don't know how to calculate C exactly. I can calculate it perturbatively, and I've written several long papers on how to do that, but I can't give you the exact answer, and no one has been able to do that in closed form, okay? But you can show that there exists this C operator. Okay, so what about probability? Here's
may I interrupt and just ask? So let's take this 2x2 matrix with your two boxes,
yes.
or the equivalent of the two boxes. What is the C?
Yes.
What is C there?
So I can't give it to you exactly, but if you like, I will. It's easy to do that, and I'm going to show you how to calculate it. The C operator is a 2x2 matrix, of course, and the 2x2 matrix commutes with the Hamiltonian, and it has a very simple form. Okay, and that's one of the examples where you could find the C operator exactly in the PT unbroken region where the eigenvalues are real. And I'm going to show you the equations that you need to solve to find C. They're very simple. There are three equations. The first equation is that that C is a reflection operator. Okay, so the first equation says C is a reflection operator like parity. So that says that C squared equals 1. Very simple, okay? The second equation I've already told you, and that is that H commutes with C, okay? So if you're doing it for your 2x2 matrix Hamiltonian, you're looking for a matrix C that commutes with your Hamiltonian, okay? And the third equation is that C itself is PT-symmetric. That means that C commutes with PT. Okay, so these are three equations, three simultaneous equations. You have to solve those equations. So if H is a 2x2 matrix, you're looking for a 2x2 matrix C, which commutes with the Hamiltonian, whose square is 1, and that commutes with PT. And it's very easy to do that. If you could do it, if you want to have fun, you could do it yourself, and you will be able to do it in 15 minutes. I promise you. You just write down the most general Hamiltonian whose square is 1, that commutes with the Hamiltonian, and so on, and commutes with PT, and you will be able to calculate C. Okay, that's easy to do. Now, once you have the C operator, I'm going to answer the question about unitarity. Okay, so let me present it to you as a just give you the answer. The answer is that you have to define the inner product for this theory correctly. Okay, so what is the inner product? So when you learn quantum mechanics, you learn that you have states that are called kets. Okay, and these kets satisfy the Schrodinger equation. Okay, so if they're an eigenstate of energy E, you would write it that way. Okay, and then from the ket, you construct the dual space of the kets, which is called a bra. So this looks like this. And the question is, what is this bra? And everybody knows that the bra is what you get if you take a ket and you take its Hermitian conjugate. Okay, so the dual space consists of all the vectors in the original space, and you take their Hermitian conjugate.
Yeah.
And that gives you the dual space. And then if you dot a vector in the space with a vector in the dual space, that is, you calculate the norm of the vector, that is time independent. And that's the basic, some people would regard that as the most basic principle of quantum mechanics, that says that, that the theory is unitary, okay? It took us a long time to understand this, but the problem here is that each different Hamiltonian has associated with it its own inner product. What is the inner product? Okay, it isn't dagger.
Mm-hmm.
Okay, because dagger is the adjoint for a Hermitian Hamiltonian. So what is the thing that corresponds with dagger? The answer is it's CPT.
Mm-hmm.
That's what it is.
I see.
Okay, so given a ket, which is called, given the ket, which is called E, to make a bra, what you do is you take this, you take the ket, and then you operate on it not with dagger but with CPT. Okay,
Mm-hmm.
so instead of dagger, it's CPT. So let me present this to you in a story. I like to tell this story when people ask me about this. I say, suppose you invited a speaker to your colloquium series, okay? And the speaker is talking about general relativity, okay? And suppose the speaker began his talk with by saying, let's assume that G mu nu,
Mm-hmm.
which is some metric, we'll take the metric in curved space, G mu nu, to be this 4x4 matrix. Okay, so the guy walks into your colloquium and says, I'm going to assume that the metric is this 4x4 matrix. You would laugh at the guy. You would say, wait a minute, you can't do that. You have to compute what the matrix is. Okay, it's a long calculation. You have to use Einstein's equations and determine what is the actual metric. You can't just hypothesize that the curvature in space is this. You actually have to determine it. But in quantum mechanics, that is exactly what we do. Okay? Before we even look at the Hamiltonian, we think we know what the metric is. That is, the metric is psi dagger psi.
Mm-hmm.
And what I'm saying is that if you have a more general kind of Hamiltonian, a PT-symmetric Hamiltonian, the PT-symmetric Hamiltonian has to tell you what is the correct metric to use. Okay, and the correct metric to use is determined by calculating the C operator. And that's how this works. And it turns out that once you calculate that operator, then you know that you have satisfied all of the fundamental principles of quantum mechanics, namely that the Hamiltonian is PT-symmetric instead of Hermitian, that it's in an unbroken region of PT-symmetry, and now we know that the theory is a unitary theory. It conserves probability measured by the appropriate metric. And by the way, of course, that metric has to be a positive metric and so on. And it's easy to show that this metric is time independent. And that's because PT commutes, you see, PT commutes with the Hamiltonian and C commutes with the Hamiltonian. So the usual proof that it's time independent, the time evolution operator is, of course, e to the IHT, but you have to show that CPT commutes through, and it does. Okay, and that's the reason. The reason is that C commutes with that Hamiltonian in the exponential, and PT commutes with the Hamiltonian, and that's how it works.
Yeah, sorry, but I mean, this again, what this does is that it brings in linearity into quantum mechanics and keeps that linearity there.
Indeed.
But your probability could even be conserved once you introduce nonlinearity into quantum systems.
Yes.
And so, I mean, what makes one better than the other in some sense? And this was my whole question about the structure of quantum mechanics. because what you're maintaining is the linearity. You're maintaining the Schrodinger equation.
Yes, you're absolutely right. And in fact, it is really interesting. Every time I give a talk on PT symmetry, there are some experts in the audience who are experts in some area of physics, and you may be an expert in nonlinear quantum mechanics and the equations of nonlinear quantum mechanics and so on. And usually I find that a week or two after I go away from giving a talk, somebody writes a paper on PT symmetry in their area. I mean, if it's somebody who's an expert on scattering theory, they write a paper on PT-symmetric scattering theory. Okay, it doesn't matter what it is. So PT is not a problem, but rather it's a concept. It's like a laboratory in which you can bring your expertise and study PT-symmetric systems that you have already understood very well in conventional quantum mechanics, okay? And I invite you to do this. There have been, I can tell you, I'm not an expert on this, but there have been a few papers that people have written on systems of nonlinear, not linear, but nonlinear quantum mechanical systems that have PT symmetry, and they have discovered some interesting properties. And I can put you in contact with those people if you're interested. But only very, very little has been done. And I'm sure if you think about it, in some sense, I probably shouldn't put you in contact with anybody because very little has been done. And if you're an expert on nonlinear quantum mechanics, you can right away, I mean, PT symmetry is very simple. And right away, you can start studying it and finding out the properties of nonlinear quantum systems instead of linear quantum systems. And I'm sure you will write an absolutely beautiful paper, and I would love to see the paper. Okay, so I agree with you. I have only been talking about conventional linear quantum mechanics described by linear operators, where the Hamiltonian is a linear operator and the Schrodinger equation is linear and so on. And there's absolutely no reason not to study nonlinear PT-symmetric systems. I can say this, people have studied PT-symmetric nonlinear wave equations, and PT-symmetric nonlinear wave equations are fantastically interesting. Like the nonlinear Schrodinger equation. And you can even construct, there have been a bunch of physical review letters written on the discrete PT-symmetric nonlinear Schrodinger equation. It is fascinating. It has remarkable properties. I can't even begin to tell you about it. It's a very long story. One of the authors of the paper is Ablowitz, who has worked on nonlinear waves his whole life. Okay, when I was an assistant professor, he was an advanced graduate student working on nonlinear waves at MIT. And he still works on nonlinear waves. So I mean, you can study all kinds of wonderful problems. Okay, in fact, I wrote a poem about this. Maybe you want to hear the poem. It goes, if you're looking for problems to do, here's my advice to you. Replace hermiticity by PT-icity and begin your research anew. Okay, and that's all I'm saying. Everything that you are already an expert in, I mean, let's say, for example, you're an expert in fermions. Okay, you have studied neutrinos. Well, you can now study PT-symmetric neutrinos. It is really interesting that as I'm sure many of you know, neutrinos have the property that they oscillate, okay, that they have spatial oscillations. Neutrinos, solar neutrinos, neutrinos that come from the sun, have spatial oscillations that have been measured, okay, and it has people who work with Hermitian quantum mechanics have concluded that because they have species oscillations where over a period of space, many meters, they become a different species of neutrino because they oscillate. That implies that neutrinos have mass.
Mm-hmm.
However, you can write down a PT-symmetric Dirac equation, and what you find out is that neutrinos can have species oscillations but still have zero mass. The PT symmetry allows the mass not to change, okay, which is quite fascinating. So in fact, even though we clearly have measured neutrino oscillations, the neutrinos may not have mass. And you could study PT-symmetric gravity or PT-symmetric electrodynamics. In a theory of PT-symmetric electrodynamics, you know, in ordinary electrodynamics, a positive charge attracts a negative charge, but a positive charge repels a positive charge. But in PT-symmetric electrodynamics, two positive charges attract and two opposite sign charges repel, which is really interesting, okay? Furthermore, while ordinary electrodynamics, quantum electrodynamics, is not asymptotically free, and therefore a lot of people regard it as a trivial theory, PT-symmetric electrodynamics is asymptotically free. So this is an example of a theory which does not have a Yang-Mills symmetry and is still asymptotically free, okay, which is quite interesting. In a theory of PT-symmetric gravity, two masses repel instead of attracting. And that's very interesting because if the correct theory of gravity has a short range effect, which is just Einsteinian gravity, and a long range effect, which is PT-symmetric gravity, then that could possibly explain why it is that the universe at great distances is accelerating, while the universe at short distances is attracting. Okay, I mean, there's a tremendous amount of work that can be done by experts in that field, and introducing PT symmetry is really elementary. You can be doing PT symmetry in whatever your research expertise is in one day. It takes you no time at all. And then you'll be writing papers. Think about all the new papers you can write.
Okay.
Thank you so much.
Thank you very much for this very interesting and substantial answer. And now we see definitely that, of course, if we extend lots of notions of Hermitian physics into the non-Hermitian world, then lots of surprises can wait ahead. That's for sure. What is also for sure is that we took almost 2 hours already, which means it is now going into the deeper night in the yesterday in Professor Bender's place, and actually close to lunch in the future from where we are connected to. But we have one maybe last short question by Dario Rosa, who raised his hand. I'm not sure if Dario, if you are still there, please go ahead and ask. Please, both sides, question, answer, try to.
Okay, yeah, it should be fast. I mean, it's about, I mean, how to recognize which of, I mean, when the breaking of PT symmetry appear or not. Now, if I mean, let's go back to the example that Sergey was discussing, the one. Now, if I understand correctly, with the correct boundary condition, the theory, I mean, has real eigenvalues because somehow one of the two edges under PT is mapped to the other edge, right? I mean, when you do
What do you mean one edge? I didn't understand. One edge of the theory?
I mean, in the theory in which you have the quartic potential with the wrong sign.
One wedge. I see. I didn't check here. Okay,
Yeah.
yes.
Okay,
yes,
so
that's
if
right.
I understand correctly, probably in the case epsilon smaller than 0, there is no way to make the two wedges connected by PT, and so you get complex eigenvalues in that case. Is it correct, my understanding?
That's right.
Okay.
That's right. So those, and that's because you're talking about an upside down potential, which has unstable states, and therefore it has complex energies.
Okay. Okay, that's it. Okay, yeah. Thank you very much.
Yes, that's right. That's right. That's right.
Okay. Then it looks like there are no further raised hands, and I would then suggest that we come to the finish, and we thank very much again to Professor Bender for this very exciting, seemingly very simple, but actually very sophisticated when it comes to all the details topic explained to us on PT symmetry. And we wish you still a couple of hours of happy hours of your birthday, or actually birth evening then now, or birth night, whatever we want to call this. And
well, I will tell you a secret. My wife, while I was talking, has just baked me a birthday cake.
Oh, this is fantastic. So then good appetite. Enjoy your birthday cake. Apologies to your family from us that we were withholding you from them. I hope we all enjoyed, and I thank all the audience for the participation. And and that is then the end of this. Thanks again.
Okay, it was a pleasure to visit you, if only virtually.
And let me add, and we will look very much forward to have you physically here with us, because I'm sure that will induce a lot of further discussions and discussion sessions.
Yeah,
So
I think that would be lots of fun.
Thank you.
Both my wife and I love to eat Korean food, and it would be nice to have real Korean food.
Okay. Excellent. So let's have that as a plan, a post-COVID plan. Thank you very much.
Terrific. Okay, very nice to meet you all.
Stay healthy. Bye-bye. Thank you.